All right. Looks like they've closed the door, so I think we're ready to get started. Christine, are we good?
Yeah, you're good.
All right. All right. So good morning, folks. Thank you for attending. This is Debugging FIDO at Scale. I guess I need to be over here because I don't have a clicker. Is there a clicker for the...
Bring your own clicker, Dave.
Bring your own clicker. Okay, cool. BYOC. No clicker. Okay. All right. Well, I'll just run the slides from up here then. All right. Great. Good morning. We are here talking about debugging FIDO at scale, and my name's Dean Sachs. I'm a senior security engineer with AWS Identity, and I'm here with my colleagues. Is that on?
Okay. Hey, I'm Jamin Bhatt. I'm a senior software engineer in AWS Identity.
Hi folks, this is Jugal Keskani. I'm currently a software engineer with AWS Identity.
Great, thanks guys. So we collectively have been involved in the FIDO Alliance, myself for over 7 years now. Jamin's been working with the FIDO Alliance for 2 or 3 years now. Collectively we have over 10 years experience in working with FIDO technologies, U2F, FIDO2, and of course passkeys. And so what we're going to talk about today is passkeys and how to debug them at scale. But more importantly, I need to let you know what we're not going to talk about. We are not going to talk about how to implement FIDO. There are other master classes this week that talk about implementing FIDO. There are lots of good talks to see and plenty of resources online like passkeys.dev and of course the FIDO Alliance site. But we do expect that you start with some familiarity with passkeys. If you don't have, or sorry, I should say FIDO. If you don't have familiarity with FIDO in general, this may not be the best talk for you. And I'm not telling you to walk out of the door. That would be terrible. But just I want to set expectations for the audience here. So let's start with what the problem is. So the problem with debugging FIDO, and specifically debugging it at scale, and working at AWS, of course we have some massive scale, is that many of the implementers right now are new to this ecosystem. They don't have a lot of experience with FIDO. They haven't been using it for a number of years. Maybe they're being pressured into supporting passkeys now because, of course, passkeys are on the rise. And so there's a lack of experience in the industry. And we have a huge array of authenticators, browsers, libraries, and configuration options. And there can be bugs in each and every one of these. And so this makes these bugs somewhat difficult to track down because they are relatively rare. And they may depend on a specific configuration of a specific host with a specific FIDO authenticator in order to trigger that bug. And it can be really hard to track some of these down. And we've had some interesting experiences in debugging some of these, both for our customers publicly as well as for some of our internal executives who've run into some edge cases with FIDO. So let's take a look at what a FIDO deployment looks like. And this is a very simplified, high-level diagram of what a FIDO deployment looks like, because you need to understand all of the places where bugs can occur. So first we have the user, and the user has an authenticator. And I must say, I am using the Identicons here. These are one of the gifts my friend Vittorio Bertocci left our community before he passed. And in this icon set, what we're showing is a FIDO authenticator. Looks a lot like a YubiKey or a hardware security key, but don't fool yourself. This is not just a hardware security key. This can be any FIDO authenticator. It can be your iPhone. It can be 1Password, Dashlane, Bitwarden, a hardware security key like the Yubico key or Talis keys. So anything that does FIDO authentication fits here. Of course, the user communicates with the browser. And the browser is where they are seeing authentication requests as well as registration requests. And there has to be a communication pathway between the browser and that user or the devices, the authenticators the user is using. In general, you are going to be using what is called CTAP, the Client to Authenticator Protocol, and you don't have to know anything about that if you're an implementer. But CTAP is the protocol used between hardware keys and browsers. It's also used in the hybrid flow, where you get the QR code that you scan from your phone to be able to authenticate on another device. Of course, your browser is communicating to the relying party. The relying party is the website that you want to log into or you want to register a credential with. And this relying party probably has some sort of a database backing it to store your credentials and other metadata about you or its users. And this is, in some cases, when we are using what is known as attestation. Attestations are statements of fact about a thing. When we're using FIDO attestations to prove where a hardware security key has originated or what its properties are, we need to be able to get that data. And that data is stored in the FIDO MDS service. Now, I show this here as a separate service, but in reality, what we do is you cache the MDS data locally. You don't want to reach out to MDS live in real time, but you cache that data locally. So if you are processing attestations, generally speaking, only available on hardware security keys with some limited and TPMs with some limited exceptions. If you're processing these attestations, you need the data from MDS to be able to process them effectively by, say, pulling out the keys that are used to sign over the attestations so you can validate the attestations are correct. And of course, somebody has to insert data into MDS, and this is the manufacturer. So this could be Google for the Titan keys or Yubico for their keys, or whomever the manufacturer is that's inserting their data into MDS. Now, the reason I show this is because each of these areas can have bugs. And we have to know how to figure out where that bug exists. And this can be actually quite tricky, as we've learned from some of our experience. Because we have a Cartesian product of debugging. And I'll tell you this slide is wrong. I confirmed with Paul Heim at the FIDO Alliance. There are about 360, I believe, L1, L1 Plus, and L2 certified hardware devices in the FIDO ecosystem. L1, L1 Plus, L2 represent different security levels of ever-increasing complexity. And so we've got these, say, 360 hardware security keys. We've got another 23 passkey providers that are in the passkey provider database maintained by Tim Capali. And we've got about 6 operating systems: iOS, iPadOS, macOS, Windows, Chromium, or Chrome OS. Linux, of course, could go in there too, or various forms of Linux could go in there. And 4-ish major browsers that cover 95+% of the market. And so if you do the math, you're looking at over 10,000 potential combinations here. Now, by a show of hands, how many of you are going to test all 10,000 of these combinations when you're rolling out passkey support or FIDO support? Right, none of you, exactly. Because it's nearly impossible to test this. And that means you're going to run into bugs in production. And so with that, I'm going to pass this off to my colleagues, and they're going to start talking about how we debug browsers.
Thanks, Neen. So next we'll talk about debugging browser-specific issues. These are some of the real-world examples that we faced at AWS, and I'm going to talk about some lessons learned as a result. Oh, okay. All right. So as passkeys are evolving quickly, we are seeing inconsistent behaviors across browsers, and we are anticipating some breakage in the upcoming ones. So if you go to passkeys.dev, you would already see that there is inconsistency between like sync passkey support, autofill support, or cross-device authentication. So in this incident, we specifically had issues with user verification bit. So user verification flag is a request parameter in the FIDO WebAuthn request, and it conveys the RP's or relying party's preference about user verification. User verification here can be biometrics or PIN, and there are 3 possible values: required, preferred, and discouraged. So required means the RP wants to always do user verification. Preferred is a best effort. For example, if your laptop's lid is closed and biometrics is not possible, a browser won't fail that authentication attempt because user verification cannot be completed. And if it's discouraged, then RP doesn't care if the user verification was done or not. Oh, okay. So okay. All right, so initially we saw issues between Chrome on Mac and Safari, where Safari with preferred flag, if the laptop's lid was closed, wouldn't prompt for user verification, versus Chrome on Mac was always prompting. With Chrome 1.1.3, a new change was introduced where it started skipping the user verification in cases where authenticator was unavailable. The side effect of this change was customer perceived this as a security downgrade because previously they were always seeing user verification challenges, and now on some occasions it wasn't getting presented. And we had to do like proactive customer messaging to explain them like this is a browser behavior change and it's not a security downgrade. Another issue following the same theme, it's breaking backwards compatibility regarding attestation. So attestation statements are included in the response from the authenticator, and this typically certifies security properties of the attestation. And there are 4 possible values: none, meaning no attestation; indirect, that means like it's an anonymized attestation, where the authenticator's make and model is not recognized. Direct means it's an explicit attestation. You can actually pull the attestation's GUID out and then look it up in the FIDO metadata service, and you can fetch the security properties of it. Enterprise attestation is something not relevant here, but it's something supported through MDMs. So the issue that we faced in attestation is AWS IAM currently always requires attestation during registration ceremony, and Firefox introduced a change where if advanced privacy setting was switched on, then it wouldn't send the attestation, even if the RP said it needs a direct attestation. So this change broke all the registrations, MFA registrations for AWS. Since then, the bug was immediately fixed, but we expect to see such issues happening frequently for a few months until the passkey ecosystem stabilizes. So we have some lessons learned here. I think the first lesson learned is typically when you implement FIDO, you would use standard libraries, and these libraries come with defaults. And sometimes these defaults don't actually meet your customer needs. For example, the default user verification is preferred, but some of our customers complained when the behavior changed and it wasn't always requesting user verification. So test the default behavior, see what your customer requirements are. The next lessons learned is you need to have mechanisms to consume browser change logs. And these are some of the links. Passkeys.dev is also a good resource. It has a table enumerating different browsers and what features are supported in those browsers. The third lesson is engagement. So when you do discover issues with browsers, how do you reach out to them, or how do you report bugs? So these are some helpful links. You can proactively reach out to those for those issues. And I think the most important lesson learned here is monitoring. So we have 3 pillars for AWS: security, availability, and durability. So as part of the availability pillar, we try to detect issues as soon as possible and quickly try to mitigate them. So we retrospectively reviewed how can we improve detection of such issues, and we came up with a solution to use high cardinality metrics using AWS CloudWatch. What this means is now we have data on per browser and per authenticator success rate. So if one of them goes down, for example, if Firefox is having issues with one of the passkey like Google, then it becomes a trivial task to identify those issues. Next, we'll talk about debugging authenticator specific issues. So the first, the theme is same here as the backwards incompatibility introduced here. So on this occasion, when passkeys were announced, they were synced passkeys, meaning if you registered a passkey on your iPhone and then tried using it on your Mac, it's synced through your iCloud account and you would be able to use it. But keys created before the passkey announcement are device bound, and those keys do not work across devices. So if you registered a key on your iPhone, you won't see that key on Mac. So what happened because of this is if a customer has mix of old and new keys, then some keys won't work across devices, and then it's really difficult to explain to customers like why this behavior is there. Another such issue is when the attestation certificate on an authenticator expired. So Jugal will further explain this issue in the later section. But expect backwards and compatible changes in passkey authenticators as like the world is quickly changing. We have the same lessons learned here. So if the issue is discovered, we need to proactively engage the browser community, the authenticator community, and you need to have monitoring to know that this particular vendor's keys are are failing. Another issue we've seen with authenticators is if customers are using their hardware security keys as passkeys, then they basically have the risk of running out of space. So passkeys are discoverable by nature, and what that means is the passkey provider stores mapping between the user and mapping between the user and the RP against the key. So it requires more memory compared to non-resident keys. And for instance, in this scenario, if one of the customer was using a YubiKey and they had already registered the key on 25 other websites, when they tried on AWS for the 26th time, the key space ran out. And the other challenge we faced during this issue is the error was pretty generic coming from the authenticator. It was a CTAP error not allowed. So it doesn't really provide us information that we can tell the customer, like, this is the exact problem you're facing. Yeah, so this lesson learned is not ideal, but in this case, like, you need to have good SOPs. Like, your support team needs to know procedures and run through them one by one to narrow down the issue. But as a result of this, we started engaging with the FIDO working groups more actively, and we are trying to get new changes in that would help improve customer experience. Next, I'll pass it over to Jugal to talk about the debugging RP section.
Thanks, Jamin. Hopefully I'm doing this right. This is my first time on stage. So, hi folks. Let's start looking into the issues that you might encounter on the relying parties when you start supporting FIDO credentials. Now, before browsers started supporting WebAuthn, we were on the U2F realm, right? And on the relying parties, we were still supporting U2F. With the U2F implementation, we had certain custom serialization and parsing logic. Now, when we migrated over to WebAuthn, we decided to reuse some of those implementations. Naturally, the first set of issues that we ran into was with our custom serialization and parsing logic. So our recommendation to people moving over from U2F to WebAuthn or implementing WebAuthn from scratch, please do not reuse any of your U2F code. Neither your implementation nor any of the libraries. There are several WebAuthn libraries available on the marketplace. Please use one that best fits your need. Security controls and compliance. Now, when you look at customers, not all the customers are going to have the same set of requirements, right? Some might prefer ease of use versus the added friction due to security. And then there might be completely different set of customers which might have a different set of compliance requirements. Our recommendation is to provide secure by default design, right? And for customers in the regulated space, please do provide additional controls. Now, AWS Identity provides that via IAM policies. We enable the customers to restrict based on the authenticator security policies, like, for example, expecting FIPS compliance, right? Currently, passkeys or synced resident keys do not have any certifications attached to it in the FIDO MDS, but there are hardware security keys which have several FIDO and FIPS certification tied to it with different levels like L1, L2, L1 plus, right? So, for example, a customer in the regulated space can author a policy that you see on the screen limiting the registration to just FIPS L2 plus registered devices, right? So it would reject all the other devices that would not have a FIPS L2 certification in the FIDO metadata service. Please note, at AWS Identity, we do not reject any authenticator based on the manufacturers, but at this moment, we do require attestations. Inconsistent public key credential parameters. Now, when you are dealing with the large scale as Amazon, you probably have a different data plane for read-heavy operations. The challenge this presents is control plane and data plane can end up with different public key credential parameters. Now, for example, imagine a bad commit updating the control plane RPID to a certain value which is different from the data plane. Now, in that case, all newly registered keys would work from the registration standpoint, but they would be rendered useless when the user tries to sign in with those. So, apart from standard logging and debugging procedures, anomaly detection would really come in handy. We use AWS CloudWatch embedded metrics to alarm us on these situations in our pre-prod environment. Obviously, you don't want customers reaching out when you basically messed up your control plane and data plane. Let's look at the result of the create call initiated by the web server. The credential object contains the public key and the attributes that are needed to validate the registration event. The public key credential object is then sent over to the server for certain validation steps. Now, according to the WebAuthn spec, it actually prescribes approximately a 19-point procedure to properly validate this data. That's a lot. That's a lot of validation steps, and it's easy to mess up some of those. So let's look at the recurring set of issues that you might see on the relying parties when you try to validate this registration data. The first piece of data that you would probably want to validate is the client data JSON, right? Originally, it is a U2F8 byte array, but we'll just represent it in base64 for readability. Now, client data JSON contains the challenge string, which was sent over in the browser's create API. This means that basically the relying party has to validate that the challenge string is the same as it was passed to the original browser create API. This would help verify that the registration event was not tampered with. This also means that the relying parties now have to maintain a state and persist the challenge string. The challenge string should be a random nonce and should be tied to a single registration event. This is the basic mechanism which will help prevent replay attacks. The expiry of the challenges should be a bit longer than the timeout set on the public key credential creation options passed to the browser. Now, there is no template on how to actually implement the challenge key persistence or maintaining that state. This is probably one of the reasons why early implementers might run into issues with basically not adequately verifying the challenge string, or might run into issues with where verifications fail due to user behaviors. And the user behavior can be as simple as, well, they initiated the call and they're waiting to pull out the YubiKey or a different authenticator and actually go through the biometric or the secondary verification, right? This would mean that the WebAuthn request actually timed out, and that is where you would need adequate logging and metrics to identify why the verification failed. The second piece of data that you probably want to validate is the attestation object. Same as before, it is a U2F8 byte array, and we will display it in base64 for readability. This object contains the credential public key an optional attestation certificate, and some other metadata about the authenticator. The attestation object that you would see is based on the parameters that would be passed on to the browser's create API. FMT here represents the attestation format. Authenticators can provide attestation in several different ways, indicating how the server should parse and validate the registration object. Let's take a closer look. RPs can signal the authenticator their preference to receive an attestation statement. Now, ultimately, the attestation statement format is chosen by the authenticator. The example uses a packed attestation statement format. Here, the X5C field contains the attestation certificate, which can be used alongside the attestation root certificate from the FIDO MDS to cryptographically verify that the device is genuine. Relying parties might choose to allow only certain authenticators based on additional metadata that they might find for these particular authenticators in the FIDO metadata service. AGUID can be used to look up the FIDO metadata service for these authenticators. On the right-hand side, the attestation statement format now is of the type none. Naturally, there is no attestation statement. Now, surprisingly, these are from the same authenticators with the same public key credential parameters passed to the browser. The only difference was the browsers. One was on Chrome and the other was on Firefox. So when you request direct attestation on Chrome, you would get a packed attestation statement, but on Firefox, you would get none. So if the relying party was allowing only certain authenticators based on its metadata or properties, the same authenticator would work on Chrome while it would fail on Firefox. Now, this is where high cardinality metrics will help catch such issues, right, on your production environments. The poor authenticator metrics will help you analyze that which authenticators are not working on which browser, and that way you can potentially debug such issues. We have also got several reports suggesting that allowing Chrome's WebAuthn emulator or allowing self-attestation was deemed as less secure implementation. This ties back to our conversation where we give customers the control to allow or reject devices. At AWS Identity, customers can author policies based on the device's security policies, security features, right? Basically like FIPS certification or FIDO certification, and that's how they can restrict registration to only certain devices. Now let's look into the issues that might run into because of verifying the metadata of a certain authenticator. We looked at where we can get the AAGUID of an authenticator from and how we can use that to actually look up the authenticator's metadata from the FIDO metadata service. The attestation root certificate that you see over here can be used by the relying party to cryptographically verify the credential public key came from the same device. The recommendation from FIDO Alliance is the relying parties should update the FIDO metadata service cache, right, at least once per month. One of the issues that we encountered was with Google Titan v2 key in the data in the FIDO metadata service. The attestation root certificate associated to Titan v2 key was actually incorrect or expired. So if the relying party was actually validating the certificate chain of the Titan v2 key by using the attestation root certificate from MDS as a trust anchor, the registration event would fail. This is where, again, high cardinality metrics and poor authenticator metrics would potentially help debugging this issue. When you run into such issues, our guidance is to reach out to the authenticator manufacturer and at the same time also reach out to the FIDO MDS contributors. I'll pass it back to Jamin, who can summarize the learnings for us today.
Thanks, Joel. All right, to summarize the learnings, first is architecture considerations. If you're building FIDO RP from scratch, one of the things is don't implement your own parsing, encryption. Just use standard FIDO approved libraries. It will save you a lot of complexity, code, and time. If you're dealing with as large of a scale as AWS, you're probably separating your data plane from your control plane to separate the read-heavy operations. Make sure your web auth and request parameters are consistent, because if your data plane and control plane goes out of sync, then it's going to cause an outage where customer registers a key successfully, but then when they try to log in, it doesn't work. In instrumentation, I think we talked about it multiple times, but having good high cardinality metrics that can help you narrow down the issue to specific browser version, specific OS, and to specific authenticator types will save time and help customers quickly resolve the issues. One other thing we recently did in our AWS Identity Center login is we introduced request tracing. So when a request fails, we will display a request ID along with the timestamp on the error page. And this can help because customers will typically provide you the screenshot. And then with that request ID, we also make sure all the distributed systems or microservices supporting that request use the same request ID. So that helps you narrow down the problem and avoid like a huge potential log dive. Have mechanisms to consume browser authenticator, change control, and have procedures to reach out to them in case something breaks. And lastly, understand your customer needs. Not all customers are same. Certain customers may require a higher degree of assurance, and you need to provide those controls to the customers. For example, the IAM policy that we saw for enforcing FIPS compliance, that is one example of how AWS is helping customers who are in the tightly regulated industries. So that's it for today. Thank you, and we will take some Q&A now.
So if there are any questions, please raise your hand. I think Lorraine's going to bring a mic around. Jeff.
Thanks for the session. Question, so earlier you'd mentioned instrumentation and exposing some of these metrics through CloudWatch, and it kind of sounded like maybe that was internal. Is that also functionality that is exposed externally in CloudWatch so that customers can see when a passkey was registered, if UV occurred, what the attestation data is, and things like that?
Well, I'll answer part of that, and then I'll pass it to Jamin. In the FIDO specifications, you can so with user verification, I know you're speaking about this a little later. User verification, it's only passed the flag. You don't know if it was a biometric, if it was a PIN, if it was a password, right? You never get exposed that set of information. You might be able to infer it based upon the device if you have an attestation from the device when it was registered, but you're not going to see that by default. As far as the metrics, I'll pass it over to Jamin.
Yes, I think there's two parts of it. First is, if you register something on AWS, an authenticator, you will see that in the CloudTrail event with the attestation data. And to the second question, if this works out, the CloudWatch metrics work outside of AWS, and yes. So we use CloudWatch contributor insights. As long as you start feeding your logs into CloudWatch and enable contributor insights, and then you need to configure a rule to parse out certain fields. So we actually started with a rule that sends us an alarm if 25% of MFA logins coming from a specific browser starts to fail, and then you can basically tweak your rules and make them more efficient. I believe they also launched anomaly detection recently. That's something you can try and count more, and we are currently experimenting with that.
Yeah.
Go ahead.
That's me. Good point about the cardinality that you mentioned. There you can kind of get insights on how different browsers behave, etc. But let's be realistic, right? I do want to make sure that my customers are using an approved device. I want to check against the MDS. And I see that Firefox is not sending me attestation data, like because it's a packed format, not packed format. What do you do ultimately? Do you just drop Firefox?
Interesting question. Our customers are public, right? We can't control which browsers they use. We support whatever browser you bring within some level of reason. In this case, there were actually 2 instances of Firefox breaking. And in those 2 instances, they were bugs. They were bugs in Firefox that we and others, including some hardware key manufacturers, reached out to Firefox and worked with Firefox to get those bugs resolved. That came back in a regression later, and that's why we saw it twice. But it does, last I looked, I didn't see any issues. But this was specific to, I think the first one was Firefox 1.14 on Mac OS. So it was a really narrowly scoped, like, okay, Firefox is maybe 5% of the market, and then you've got it on Mac OS. And so you're looking at a narrow swath of users using hardware security keys on Firefox with Mac OS using a certain version of CTAP and chain all of that together, and then you get a bug, right? And this is why it's so incredibly difficult to debug some of these things, because I can ask my customer, well, what kind of authenticator are you using? Oh, it's a Yubico device. Okay, well, what version? What version of CTAP? And then start running through all of the questions. What version of Firefox? What OS are you on? And then it's a matter of, oh, it's a Yubico device. Do they have any notifications? Can I reach out to my friends at and some of the advantages of being part of the FIDO Alliance is I have a lot of friends at Yubico, and I can reach out and go, have you seen this? That's not necessarily available to everyone. So you have to use bug reporting for all the browser manufacturers. You can look on, I've seen bugs reported on Twitter or whatever it's called these days. Doesn't really matter. I've also seen it. Pop up on LinkedIn, and then we've had direct reach outs from customers or direct reach outs from people in the alliance. So you have to use all of the resources available to you, but predominantly look at bug reporting. Apple's Radar system, Chrome has a system, Firefox has a system too. Look at those and follow the work that's happening there and what releases have happened, because that may give you insight as to where this bug might be coming from. Does that answer your question? Yeah. Great. Cool. Sir?
Yeah, so you were talking about testing all the use cases, and yeah, that's impossible. So what about, though, when you do have a certain set of authenticators you want to play around with and check? Are there any tools that you guys can recommend to use that are closer to the client side to help with the debugging? I remember just when I first started playing with passkeys, like you were saying, you go through the browsers. I hadn't used it before, and I was using it on a desktop, and I didn't have Bluetooth on there, and it wasn't working. And I didn't figure it out until I actually switched third, fourth browser, and I saw some type of signal. Then I went to Stack Overflow and figured out, oh, it needs Bluetooth. Put a dongle in there, it works. So are there any tools?
Yeah. So on Chrome you've got the WebAuthn debugger that's in there. I like using WebAuthn.me or WebAuthn.io. WebAuthn.me has some good tools for debugging and seeing, I sent these options to the authenticator. I received this answer back. I know the three of us have spent a lot of time with that at times, looking and going, well, wait, what's different between the hardware key I have, the hardware key you have, the hardware key that somebody else has, and really trying to run down the differences. Because in one case where we started looking at this, some of the hardware keys we had were CTAP 2.1, some were CTAP pre-2.2, and those differences are really, really important. But you only discover them when you can find that, oh, I've got a different key than Jamin has, and he's seeing different results using the same browser, same OS, etc. And so you kind of have to spend a little bit of time. One, if your customers are using hardware security keys, like at home, I have a bucket of these things with all different kinds of versions, all different kinds of formats from all different manufacturers. I have a keychain, I can shake around. It's like a janitor. So you have to have a bunch of test devices potentially, but you're probably not going to have every device that your customer has. And so you need to establish good rapport with your customer to say, help me help you. give me as much information as you can. And if you know, say they're using a Yubico device, they can use the tools from Yubico to be able to pull out some of the metadata about that device. If you don't have that, other manufacturers will have similar tooling. So you need to really work with your customer to figure out what they have and all the parameters of their configuration. There was the advanced, not advanced protection. What was the advanced? The one that the security settings that silently changed with the release of one of the browsers that impacted the ability to get attestations. Like, oh, you updated your browser yesterday, and then this broke. Okay, that's a clue. And so there's a lot of hunting for clues here to debug this, and that's what makes it particularly frustrating.
Enterprise sounds like it's going to be fairly easy to do, but
Yeah.
Can
Well,
you repeat the comment?
Yeah, what was said was in the consumer space this is probably really difficult. In the enterprise space, probably easier. And I would agree because in the enterprise space, you might go buy 50,000 devices from one manufacturer and they're all configured the same, and you know what browser configuration you have because your browsers are all configured roughly the same. So that is certainly easier. The challenge in the consumer space is you don't know what they're bringing to the party, and the consumer may not know what they're bringing to the party either. They may not understand the nuance and difference between a passkey. So they're using Chrome and they're using passkeys happily, and then one day everything breaks because Chrome switched over from using its own internal passkey implementation to using the macOS iCloud implementation, and the customer may not know that. And so these are the kinds of things that we in this field have to sit and watch and understand what's happening and how things are breaking, and then communicate as proactively as possible with our customers to ensure that they don't get broken by something that they are not in control of, at least not directly in control of. They can control it once they know about it, but things are changing rapidly in this ecosystem, and those are some of the rough edges that we're running into today.
Dean, over here.
Yeah. Hey.
Yes, sir.
So I just wanted to build on what you said. Let's take this one scenario of example.com. I'm using Chrome to authenticate. I created a passkey on example.com, and then I used a password manager like 1Password to sync it over, and then I tried to log in on example.com using Firefox.
Mm-hmm.
Is that gonna work? Because like I saw there's some attestation statement that's needed for like from Chrome or something. Like I'm just curious about like the sharing of passkeys and the syncing of passkeys between browsers.
Sure.
How does that work?
So first things first, when it comes to synchronized passkeys, and you can go find the talk I did last year at Identiverse. It's on YouTube, on the passkey threat model. And one of the things that you'll learn is synchronized passkeys generally do not carry any attestation statements. Attestation statements in the FIDO ecosystem are provided when requested by the RP, when allowed by the user, and when supported by the authenticator. And so today, in the consumer market, there are 0 passkey providers that support attestation. And that's okay, because if you're using it as a password replacement, it's still a better password replacement because the properties of the passkey are better than the properties of a password. However, the other part of your question that is the more interesting part is, if I store a passkey in 1Password on Chrome, can I now use it on Firefox? And the answer is yes. All of the passkey manufacturers, and I know at least a couple, I see at least one over here, they synchronize not via the browser, but via their own APIs, and then the plugins are just using whatever passkey is available to them. And so you should be able to move seamlessly if you're choosing a third-party passkey provider like a Dashlane or a 1Password or a Bitwarden between their instances on different browser instances as well as across different devices. Right? And so that's personally what I do. I used 1Password, their implementation across all of my devices, whether it's iOS, macOS, Windows, whatever it is. And I have all of my credentials everywhere that I need them at all times. Got it. All right, I think we're at time. So thank you very much for your attendance. I really appreciate it. And I look forward to seeing you again in future sessions. Thank you all.